Every year, thousands of cars finish up in the breakers' yards. The main cause, apart from accident, is corrosion. The mild steel, a form of iron from which cars are made, is changing into rust.
My name is Judith Jackson, and my job is writing about motor cars. Today I'm going to show you how scientists find out about corrosion in cars and how they try to slow it down. Because one thing you should know from the start, you can't stop this sort of corrosion.
This car is typical. The sills are particularly important. One on either side of the body, they strengthen the body. And if anything happens to them, the body buckles, bends, and finally collapses. Water collects inside the sills, and this is the result. Another place where you get a lot of corrosion is behind the wheel, where all the water and grit gets thrown up. Now, it's usually a few years before a car body gets into this state, as badly corroded as this, mainly because when it was new, it was covered with layers of paint. But there's one part of the car that is completely unprotected and quickly begins to change. Exhaust pipes are one of the first parts of the car to begin to corrode. Some motorists have a new exhaust system every year because they're so completely unprotected. The exhaust pipe, like the car body, is made from a form of iron called mild steel. And when this steel corrodes, it turns to rust. If we're going to stop some of this rust forming, we have to know some of its causes. So here's where an experiment will be useful. You need 2 strips of mild steel. Put one into tap water, the other into water that has had the air boiled out of it. Leave them to stand for a time, and you'll find that the piece of steel in the tap water will become rusty and pitted. It corrodes. The piece of steel in the water without air is unmarked. So it seems that steel or iron corrodes when there's water and air about. Another place which quickly corrodes is here, around the lights, or here, where there's been a metal strip along the side. In fact, where 2 metals are together, corrosion seems to take place much more quickly. To find out about this as an important cause of corrosion, let's look at another experiment. 2 metal strips, one of mild steel, the other of copper, are put into a trough of water and then joined together by wires through an ammeter. The reading on the ammeter shows that an electric current is flowing. When an electric current flows between 2 metals like this, one of them corrodes. In this case, the steel is corroded, but not the copper. Car manufacturers nowadays try to prevent this type of corrosion by fitting cars with plastic fittings instead of metal ones. Now, there's another very important cause of increased corrosion: the air around us. It's not as clean as it looks. Unfortunately, not all motoring takes place on quiet roads in the clean country air. Most of us drive in towns and cities where industry pours smoke and gases into the air. To find out the effect of air pollution on the corrosion of steel, BISRA, the British Iron and Steel Research Association, have carried out a series of tests. This is what they did. Racks of metal samples were exposed to the weather in various parts of the United Kingdom. Let's look at 3 of the steel samples that were exposed in a polluted industrial atmosphere, and by using a special film, show you in half a minute what really happened in 3 years. The scientists decided that this rapid rate of corrosion was due mainly to a gas in the air called sulfur dioxide. To
find out more about the effect of sulfur dioxide, let's look at another experiment. This is a siphon of sulfur dioxide. Open the valve. The sulfur dioxide dissolves in the water and the electric current increases. In this experiment, the sulfur dioxide causes the steel to corrode much more quickly. So it looks as though gases which pollute the atmosphere can also increase the rate of corrosion. And there are other causes. The underneath of the car takes a real beating. It's exposed to all sorts of filthy conditions, and particularly in the winter. In winter, it is essential to keep our roads open. To help cars get a good grip and to melt the ice and snow, the local councils put grit and salt on the roads. This is very effective and makes sure that the traffic keeps moving along our main roads and motorways. But it takes a lot of salt. In the winter of 1970, Staffordshire Council put 69 tonnes of salt on every mile of its motorways. In Westmoreland, they put down 112 tonnes per mile. But Kent was the highest, with 118 tonnes for every mile of its main roads. In all, 1,600,000 tonnes of salt are put onto our roads every winter. And where there's a lot of salt about, cars seem to corrode more quickly. Here's another experiment. When salt is added to the water, there is an immediate increase in the electric current. The salt causes the steel to corrode much more quickly. Salt is by far the cheapest way of keeping our roads clear of ice and snow, and we have to use it. But the experts reckon that it helps to cause £600 million worth of corrosion every year. The corrosive action of salt can be reduced. Substances called inhibitors can be added to the salt. When an inhibitor is added to the salt solution, the electric current is immediately reduced, and this slows up the rate of corrosion of the steel. Tests by scientists at the Road Research Laboratory have shown that spending £1 million on adding inhibitors to the salt would save £6 million on the replacement of corroded exhausts. It looks like a good idea to me. Our cars would last longer and we'd get more use out of them before they eventually arrived here. We don't use inhibitors yet. Do you think we should? So we use steel for our car bodies because it's cheap and it's easy to use. But air and water are always around. We can't change our climate yet, and the steel will eventually corrode. The corrosion is accelerated by the gases which pollute the air and by the salt which we use on our roads in winter. How would you feel if you were a car manufacturer? Well, car manufacturers think very hard about all these causes of corrosion and how to reduce their effect, because they have to sell cars which are cheap and which also last a reasonable time. Let's look at the way a modern car is made and how one car manufacturer tries to protect the mild steel body against corrosion. Car bodies are pressed into shape out of sheets of mild steel. At this stage, the steel is protected with a thin layer of special grease. Different body sections are welded together, and even at this assembly stage, steps are being taken which will protect the steel. Here, under the wing, a special plastics material is put on to protect against flying stones. Strips like this help to make sure the water can't get through the gaps between the metal sheets. When the body is finally assembled, the protective coating of grease on the metal has to be removed. After this, the body is washed down and then sprayed with an acid solution. This forms a hard layer on the surface of the steel, which the layers of paint can stick to. The body is then dipped up to the waist to give it a special thick layer of paint called primer. Can you think why they don't need to dip the upper part? Next, the body is given 2 layers of undercoat. Special attention is paid to the wheel arches. The important sill boxes are coated on the inside. The underside is completely covered with a black waterproof substance which will help to protect it against flying stones. All the gaps are sealed on the inside and the body is ready for its final coats of paint. Spraying the final coats is a skillful job. Not too little, not too much, but just the right amount. Finally, a special coating inside the sill boxes. The body is now ready for careful heating in an oven, which gives the paint its final smooth surface finish. The layers of paint act as a barrier to keep the air, the water, the salt and the sulfur dioxide away from the steel. But no paint is a complete barrier, and some paints are not as good as others. In the laboratory, paint samples are carefully checked to make sure they'll stand up to the treatment they'll get on a car. A scratch is made through the paint down to the metal. A number of samples are then put into a special chamber. They are then sprayed with salt water at 36 degrees centigrade for 2 weeks. After this time, here is a good result. And here is a bad result. The corrosion has spread under the paint. Another test is in a gravelometer. A paint sample is put into the target area. Gravel chips of a fixed size are loaded into the machine. And then a 5-second burst. At the end of the test, each sample is checked against a series of special cards. From this card, representing 1 small chip, to this one, representing 75 large chips. Different cards are used until the right one is found.
Both the size and the number of the chips has to be checked. These special cards are now used by car manufacturers all over the world. But laboratory tests are no substitute for the real thing, and cars are put through many tests at this special proving ground. High-speed starts in gravel give the underside a good beating. All cars on test regularly take a dip in the salt bath, which would soon show up any faults in the paintwork. So manufacturers go to a lot of trouble to try and slow down this process of corrosion. They could do more if motorists were prepared to pay more for their cars. This car, when it's finished, will cost £14,000. One of the reasons it's so expensive is because of the materials that are used. The wheel arches are made of galvanized steel. That's steel with a coating of zinc. So too, the very important sills. But what is zinc-coated steel? How does it slow down corrosion? Let's look at another experiment. This time the two metals are zinc and steel. Join them together and a current flows. Add salt and immediately a much bigger electric current begins to flow. But this time it's the zinc that corrodes, not the steel. The steel is unaffected. This means, of course, that because the zinc corrodes and not the steel, the body won't be weakened because it's the steel which gives the body its strength. This diagram shows some of the places where galvanized steel is used, in all those important areas which are most likely to corrode first. Well, this is the finished car ready for delivery. Of course, all that galvanized steel is well protected with layers of paint, and the underside is coated with a thick layer of that black waterproof substance. After all, for £14,000, you don't expect a car to corrode very quickly. Now, despite the precautions that the car manufacturers do take, cars made from mild steel will always corrode. We can do nothing to stop this corrosion, this process of change. We can only slow it down. Well, there are plenty of ideas for you to talk about, and plenty of experiments for you to try to find out more about corrosion, not only of steel, but of other materials.
The next programme on BBC One this morning is You and Me. That's at 10:45.